Thank you, sir, for your kind introduction. Good afternoon, all. Thank you for joining the session. So I will share my screen. Just give me a second. Hope everyone can see my screen. Can someone please?
Yes, yes, we can see.
Yeah. Okay. So I'll be writing and explaining you on my tablet. Welcome to the talk on privacy preserving machine learning, which is also formally now known as federated learning. What, why, and how. I was given time of 12:45 to 1:45, so I planned like that. Now, shall I take it till two, sir?
Yeah, yeah, you can.
Okay. So, so I planned the session for first in three parts. First part would be delving deep into machine learning, um, like model centric and data centric approaches, and then getting into why federated learning is required and where it fits into the entire realm of machine learning, and then followed by federated learning, what is it and how it is done and what are the challenges. And I'll at the end I'll briefly touch upon my research area on federated learning, and that is for 25 minutes, and last 10 minutes we can have a Q&A session. To start with, let us start with something which everyone is familiar with, which is machine learning. So, as everyone know, machine learning is a branch of AI, which helps the enables the computers to train from a data and convert something called experience into knowledge, and through a process called training. So, briefly, machine learning contains the following components. So, there is yeah. So, there is basically a model. For time being, let's assume it's a black box. We don't know what model it is and what it serves. So we can call it as model or algorithm, learning algorithm or function approximator, which is mathematically called. And we pass in something called input data X, and we get a predicted output, right? And since if you're working on supervised machine learning domain, we also have a ground truth y, and the aim here is all, as you all know, to reduce the distance or the error between the predicted and the ground truth output. And we call it something called a loss function, and we try to back propagate the loss uh, through a method called gradient descent method. So, and update the parameters, weights and biases, basically, to w new as w old minus learning rate times dl by. So this is basically everyone is aware of. Now we try to understand, when I said black box, what kind of models are actually uh, currently used and what kind of task and what is exactly we are doing in machine learning. So to understand this, we can start with basically what are the types of machine learning we have. We have basically supervised, ML, unsupervised, and reinforcement learning, right? So in supervised ML, again, in discrete and continuous data space, we have tasks called classification, regression, and unsupervised, we have clustering and dimensional data direction. And reinforcement learning is again a different way of learning paradigm, which is called agent-based learning or reward agent-based learning, which tries to learn the environment and through actions, and give if it takes right actions, a positive reward is given, and if it negative a wrong action is taken, a negative reward is given, and the overall aim is to maximize the reward. Then Within the supervised, we have different tasks within supervised and supervised. And coming to the task, which again helps us in understanding the black box model. So let us start with something, an image, focusing on the um, computer vision task, let's say. So let's say I'll try to. So let's say we have a dog image, and the first task to start with is classification, which is formally known as, you can also classify anything. In this case, it's image classification, where the aim is to given an image input to a model, the model should predict it as you know as a dog. So what are the models available? CNN models, we basically use convolutional neural network models, as you all know. VGG, let's say VGG 16, ResNet 18. We have GoogleNet, we have Inception, and then ResNext, and so on. We have a lot of models, ResNext, right? And in second task, moving on, we have, let's say, we go for localization, wherein object localization it's formally called. So given the same image that we are focusing on, the aim here is to localize where exactly the object is present within that image. So we do it by drawing a bounding box within that image, and let's say the this bounding box is parameterized by four metrics. So x1, y1, four coordinates: x1, y1, x2, y2. In some cases, we try to predict x1, y1, and length, height, and width. That's also possible. So for localization, we there are models. It's also called object detection, and we have models like YOLO. You only look once. We have versions from V1, V2, I think now it's V8. So I call it YOLO family, which is again a single stage architecture, which gives us a predictions, bounding box predictions within a single pass. And on another case, we have fast RCM, region based convolutional neural network, which is again a two-stage architecture. The reason behind one stage and two-stage architectures, there is always this trade-off between accuracy or performance versus the real time. So in application domains like self-driving car, we can't wait a vehicle to we can't wait a self-driving car to detect road elements like cars, vehicles, cars, buses, traffic sign, traffic light, and so on. In some time, we want it in within seconds. So their real-time performance is very important, and models like one-stage architectures like YOLO can help in that case. In applications like healthcare, where accuracy is at most of importance, we go with two-stage architectures, and so that we can even wait for 2 days. Given any given our data, we can wait for 2 days also to get the good output. So their accuracy is more important, so we can't have any false positive that leads to a wrong diagnosis of the patient. So that's where the research is with respect to object detection or localization, to make the models more both, getting the trade-off real time and accuracy at the same time. Then third task, we have object segmentation. So as we move along with the task from classification to localization to segmentation, we are getting more and more information, precise information predicted by the model. So in the segmentation, basically, given an image in the classification, we classify the entire image as a label, a dog or cat or whatever. Then in the detection, we are giving it in a bounding box, saying that look, within the image, here is the object present, and within that, in segmentation, we try to segment pixel wise where exactly the object is present. So in this case, the dog is occupying these many pixels along with along with some empty space left out in the background. So it's clearly, it can be seen that the car is sorry, the dog is not occupying the entire pixels within that bounding box. So we do that by using segmentation. So it's also called pixel wise classification. And within segmentation, we have three different types. People working in segmentation research area might be knowing this. Semantic, sorry, semantic segmentation, instance segmentation, and then panoptic segmentation. And each have its own use cases. In semantic segmentation, we basically segment regions given in an image into different regions without trying to give instances of each class. We try to segment the entire image into regions. For example, in the autonomous, given a image or a scene, let's say this is a road and rest of it is background. So we try to segment it as entire road, and we have other regions as background. But in instance segmentation, we try to segment each and every instances of a class within the given scene again. So, for example, in the same autonomous vehicle, we segment each person or each vehicle as a different, instance of the same category. In panoptic is a combination of both, semantic and instance. We try to give regions along with instances of the classes. So, coming to the again models, since we are following a pattern of task and followed by given models. So, I'll explain. I'll give you brief, most standardly used models for each task. So instant for semantic segmentation, we have UNet and Deep Lab V3 models, which are commonly used. And for instant segmentation, we have Mask RCNN, and YOLACT, which are popularly used. In panoptic segmentation, we have uh, Panoptic, panoptic, panoptic FPN, USPNet, and yeah, Panoptic Deep Lab. Right. So this is pretty much we have for object detection. Then fourth we have object tracking. So given this, it's basically works on videos or sequence of images where we try to track an object through a sequence of images by giving it something called track ID. So we don't do a single image detection. We try to track the object through several images. So in the same example again, if you go back to the dog example, in this image the dog is located at x1 y1. It may try in the second a sequence of frames. It may have moved to some other location, but we have to give it as the same ID. Let's say ID1. So the ID1 should be common for the two frames. The location might be different. So that is where we try to track objects. For tracking, we have models. Again, coming to the models, we have DeepSoft, which is very popularly used, and then we have Tractor plus plus. Finally, these are basically pretty much with respect to computer vision tasks. Then we have sequential models where we try to work on time series data. Again, we work using RNNs. Uh,
So I had a question actually. Can we ask later or we have to ask now?
can we have the Q and A at the end? Otherwise,
Okay, sir. Okay, sir. Okay, sir.
thank you, sir. Please note down your questions because everything is written, so it won't be erased. So I can go back to exactly where you want in the exercise. Okay, RNN, GRUs, and then LSTMs and transformers. Okay, yeah, mostly used. And then finally, sixth task. I mean, I'm going into more different types of tasks. We have generative AI, which is again a very popular nowadays with the research with the advent of chat gpt. So generative ai starting generative ai can be anything: generation of images, text, audio and all. So for a generation of images, we have GANs, generative adversarial networks. Again, it has its different variants: gc gan, versus 10 gan, style gan, social gan, and so on. It has a lot variation based on its use case and research is still going on. And then I know you all know about Chat GPT, which is tries to which is a large language model, tries to generate text, and which is like generative pre-trained transformer. And then we have BERT. You know, BERT is basically sequential model. It is not into the generative AI, but basically overall we have Chat GPT, generative pre-trained transformers text. So so pretty much we have covered about different types of tasks and the different models that can be used as part of this, black box we started off here. So this all what all we have covered that comes under something called model centric AI, where we our aim is our aim is to improve the state of the art performance, and given the data, data set is fixed. For example, VG16 gave us, let's say, 95%, ResNet gives us 96%. So we are developing more and more models to improve the state of the art performances on the standard models of publicly available data set. So it comes under model centric AI, right? So and also trying to solve some trade-offs, like as I said, accuracy versus real-time trade-off. And in segmentation also, we want to increase the performance of tumor segmentation in healthcare, making it more closer to 100% accuracy. And in tracking, we want to reduce the issues of losing track IDs, or unable to detect vehicles when they are in front of when they are not properly detected, and even tracking vehicles, it's very difficult. And there is another research area which is very interesting and complex, which is multi-camera multi-object tracking. It's a hard case. Although we have a lot of models, but given the problem statement increasing the complexity, we develop more and more models to improve the performance. So that's pretty much about the model centric AI. Now we will focus on something which is very important, and which is kind of underrated, because we think every time we get good data to train models, but that is not the case. So input data, or data input to any system or process, forget about machine learning, is very important. You give good input and expect good output to any system. You give garbage and you can't expect model to train properly. So when I say input data, it has to follow some properties to have called it as rich data, so that the model trains properly. Now let us understand, this is like where our talk goes more further, and this is where um, this is where which explains the further part of how it led to federated learning and so on. So now coming to the input data part, let us assume that you are starting a new project where data set is not available. You have to collect your own data, prepare your own data, and things like that. Now, what all the tasks involved in data, coming up with your own data, and then coming up with the model. So first thing is data collection. You collect the data, or you try to generate the data. If data can't collect, you can try to generate some synthetic data, or then you try to prepare the data through, say, several sources or subjects. Okay. Now what all the challenges, we discuss the challenges. What all the challenges present in this step? This is steps involved in preparing the data. The first challenge can be unavailability of data, which is, of course, you can't get any kind of data which you're looking. Availability of data. For example, in medical domain, there's a rare disease, like only 1% of the entire population in the world gets that disease, and it's very hard to get that data. So there's chances of unavailability of data. And second, we find unavailable data, but it is imbalance. Okay. So for example, if you plot a histogram of 5 classes, um, one class is very dominant. Sorry for that. And other classes we have very less data. So you can't train a model using such this frequency. You can't train models using such data, which will be very but you'll get a biased model, so you need to do something with it unbalanced imbalanced data. Then third part, we have, okay, you got some data availability is there, and there is some balance, but quality is very poor. Again, there is a issue. You can't work on poor quality data. And finally, okay, you got some available data, it's balanced, and its quality also good, but it's very low, quantity is very low. In the same example, you in the C1, C2, C3, C4, and C5, all samples are, balanced, but they are very less data. So you can't work in this scenario as well. So then we have research areas which tackles in this domain, which called which we where we try to come up with something called data augmentation techniques, and where we use some data augmentation techniques, right? Like rotation, scaling. In the same example of the dog which we have taken, here we can rotate a dog to, certain angle and generate more data. It's still a dog. It tries to save the representation of the data. So we can use data augmentation techniques like rotation, which are very popular, the scaling, zoom, translation, and so on. And okay, data augmentation is one way. Another way is to work with uh, low quantity data. There are ML paradigms, again, research area, called zero shot learning, which where we try to work, come up with models which where when trained on no samples on that class, and we still come up with the models during the inference, which can predict the classes of data which are not even given in the training. So zero shot, we have one shot, and we give one sample again, as the name suggests, and few shot learning. So I'm rushing about these topics, so that I'm just giving an overview, so that each individual topic again is a research area, and it's a individual talk altogether. So basically, pretty much the challenges in the first step of collection, generation, and preparation we have, and then these are the solutions available, and each solution is again a research area altogether. Then in the second step, okay, you have collected the data, then you have to pre-process it, right? Pre-processing. Then again, what will be the challenges? So challenges would be, the noise is very high, that even if you try to remove the noise, the real data is also lost. Okay? So that kind of, highly noised data is also available. So a large amount of noise. And second is unknown noise. Okay, some unknown noise in some data, which we are unable to figure out what kind of noise it is, so that we can't develop some denoising techniques. However, it's still a open research area to coming up with denoising or, pre-processing techniques. So available solutions are, we have denoising, filtering. In autonomous vehicle technology, as I said, I was working on adverse weather conditions like snowy, foggy, rainy. There are techniques called de-raining, defogging, de-snowing, and so on. So there are still, it's a research area on how well can be data can be reconstructed from the noisy data. Okay, so that is pre-processing. And third step, we have pre-processed the data we have collected, and we pre-processed. Now we have to annotate. If you remember all the tasks I've mentioned earlier, like the classification, localization, or supervised machine learning comes under supervised machine learning, where we need annotations or called labels, so that we can give the models like what are the ground truth, so that it learns appropriately. So again, annotation is very tedious task, because classification, you can annotate what class it belongs to the image. But in object detection, as we move along with the higher end task detection, again, drawing a bounding box and annotating a object detection data set is kindly tedious. And then we move to segmentation. We have to augment, we have to annotate each and every pixel of the data, and it's very tedious task. Basically, the challenges here are, first is tedious task, and we need a lot of labor, a lot of human effort to do annotations. And The second is in some application domains, even if you have good amount of human resource, we can't annotate because we need expertise to annotate. For example, in healthcare, to annotate a tumor integrated brain MRI image, we don't know where is the tumor, and we need some expertise. And lack of expertise is again an issue in some task where we need annotations of a specific domain. So need manual, expertise, and most of the time we may not, if we don't find any expertise on that, we can't annotate, right? Then what are the available solutions? Again, research challenges or research areas with this, we go with something called semi supervised ML methods, where we have some amount of annotated data and large amounts of unannotated data. We try to develop models using the available annotated data and try to infer the unannotated data we have. Whatever the model gives as inference, we take them as labels. There is some large amount of error involved in it, but we are ready to take that chance. So in semi-supervised learning, we take that. Then we have uh, weekly supervised ML paradigms, and then we have self-supervised, and so on. So again, each is a research area altogether. A lot of research is going on to improve these models. Sorry, sorry. Okay. Improve these models and coming up with a better accuracy. Okay, now overall we have collected the data, pre-processed the data, and able to annotate data as well. Fourth step we is storage and sharing. Okay, storage wise, again, you can store the data within one central server, all your collected data, all your effort that you have gone through the process. Again, with respect to storage, there are different storage and training. There are different ML paradigms. Centralized ML. First one is centralized ML, where all the traditional machine learning approaches are called centralized ML. Comes under centralized ML. Then the opposite would be, obviously there will be an opposite to this thing, which is decentralized ML. And finally, we have distributed ML, right? So in centralized ML, if you take in terms of client server, there is a server, let's say C1, C2, and C3. Clients in the sense who are responsible for collecting the data, doing pre-processing and annotation. They all store the data in centralized location where model, will be trained. Some ML model will be trained. So centralized data is stored in a centralized location, and all the data, so on, all the processing happens there. In decentralized location, there is no such thing called decentralized server or something. So everything happens in a decentralized way. C1, C2, and C3, where they can talk to each other, share the data or the models, whatever they want to do. There is no such entity. In distributed ML is again a server, client server. If you talk in terms of client server setup, distributed ML is helps us to do the load balancing. The server distributes the data in such a way which has to the clients based on their computational resources, and the model will be trained within them, and model will be shared back to the server. Server performs the aggregation of trying to come up with a unified model. So here the main advantage is load balancing, not trying to give low end devices a large data set which is of no use. Okay, so pretty much storage we have these things. And finally, coming to the topic talk of topic of the talk, which is comes from this sharing part. Okay, so you have collected the data, and you have preprocessed, annotated, and stored as well in certain location, but in you want to share the data. Okay, in centralized you don't need to share, but in decentralized there's sharing happening basically. In centralized also, you are trying to share the data, clients trying to share the data in centralized location, but once it is shared, it's not like further use. But in sharing happens basically, even in the centralized you can consider, but sharing happens decentralized and distributed ML. But when sharing comes into picture, the main issue comes, which is called privacy. So there is certain data which cannot be shared, which holds the personal details of a user or someone. For example, in healthcare, patient's data is very private. What kind of diseases he has, or he or she has, what kind of diagnosis he went through, whether he has some, he is a donor, organ donor or something. All such kind of information should be very much privatized. So such applications like healthcare. Second, we have banking, banking sector. So in banking again, users or credit score or bank details, everything should be privatized. And there are a lot of such privacy sensitive application domains. And defense of a country's should be very much, data should be very much privatized. If it goes into wrong hands, anyone can exploit the vulnerabilities within a country. There will be drastic implications, right? So in these such cases, data cannot be shared as per there are regulations, actually GDPR, which is called General Data Regulation Protection Regulation, which is an European regulation, which tells what kind of data can be shared and all. Even if you have seen some interviews for the Google CEO, Sundar Pichai, questions were asked what kind of data Google says of the users and how it is processed. Then he replied, I think we have a facility of user enabling data privacy or some settings so that data cannot be shared, private data cannot be accessed. So all that comes from these regulations, and people are now very much concerned about what kind of data the third party handles, and how we are privatized and so on. So after all going through a lot of things, coming to the data centric and the model centric approaches, this comes on data. The bottleneck here is the privacy. Okay, so in the sense, on one side we have prepared the data, rich data I called as, after removing the noise, annotating, removing the class imbalance and so on. And then labeling, as I said, labeling, annotate, removing noise, and collecting good amount of data, right? On another sides, the model centric approaches, we have day by day lot of models are coming, state which beat the state of the art models on publicly available standard data sets. For example, CIFAR 10, ImageNet, all publicly available data sets. But these guys, the right hand side guys, the model developers or the AI ML model developers want to work on real time data or real world data, and to test their models on the real world, and to come up, basically to test their models on real world data and analyze its performance. So they want to work on something called real world data sets. Okay, so on one side we have good amount of data, and another side we have rich data sets. Another side there is a requirement of real world data set which these guys can provide, but in between there is a bottleneck, which is price, because of which the data cannot be shared, and things like that. So after doing a lot of effort, we end up in not sharing, so there is no point in collecting the data and keeping it with us, ourselves, right? So to address this issue, Google in 2016, I guess, has introduced a privacy preserving ML paradigm, or ML domain, which is called federated learning. Okay, so basically it is kind of distributed ML, as we distributed ML, but the only difference is, to preserve the data privacy, we can't share the data, right? So only the models will be shared between, model updates will be shared between the clients and the server. So let's say again the same example, there is a server, there is C1, C2, C3. So each clients or client devices, whatever you can call them, have their own set of data. We can't say they have same amount of data. They have some amount of private data within themselves. Now, the first step here involved is this S represents the server, C represents the client devices. The server initializes a model. Again, which model to initialize and all? Basically, all the client devices have agreed to a common task and want to participate in the federated learning or federated federation process. Basically, let's say there are all hospitals and they have some COVID data of patients and normal data as well, normal COVID X-ray data set, and they want to come up with a classifier such that it gives high performance, more than 99, 98, 99%, but they believe that the data they have, the private data they have, is not enough to come up with a better model, and they can't ask the other data set to share the data, other hospitals to share the data. Then they have commonly agreed to come up with a classifier, let's say VGG16 model or any model, classifier model. So server initializes such model based on the task which everyone is agreed upon. So first step is that initializing model. Second step is it shares that initialized model. So shares the initialized model, right? Now in the third step, each client trains that model. Let's say the same. Let's take VG16 model on their data set, on the local data set which they have for some number of local epochs. We call them local epochs. So it undergoes training, right? And then whatever the model update or the weight parameters, in the fourth step, it will share back to the server. Only the model updates, right? So in the fifth step, the server, after getting all the model updates from three clients, let's say here is also four. The server tries to aggregate them or combine them to come up with a one model, right? So the basic aggregation or the basic combination rule is averaging all the models. Okay, you average all the models. Let's say I'll denote them as local models of I is equal to 1 to n, and 1 by n. This is a basic averaging rule which the server can perform, right? So in the sixth step, the server performs something called global testing. When testing is involved, there's some kind of test data, right? So we can't call them test data, it's kind of validation data which are publicly available, which is like a representation of the client's data, which it helps us. Global testing helps us how the model has been trained, whether it is training or it is overfitting, or some data, some clients have such kind of data which is trying to bring down the overall model performance. So it's kind of helps us to validate the model's performance. And again, on in the next step, after aggregation and after testing, the server sends back the model, aggregated model, back to the clients, and it's again considered as step 3. So it again, we will look back to step 3, and the training happens. So all these all these six steps happen until the model, global model, gets converged. converge in the sense the accuracy is not more improving and so on. In the final step, seventh step, let's say, the overall trained model VGC16 is shared with all the clients, all the participating clients, which are C1, C2, C3 in our case, right? So the at the end, the advantage here is I as a client haven't shared any data. Even though I have less amount of data with me, I am able to get a unified model which gave me better accuracy, better than even if I train the model on my local data, right? So that is the advantage of participating in federated learning. It helps us to come up with a unified better model while preserving the data privacy. Okay, so that is what overall 6 steps involved in federated land. But if you also think, this is not that straightforward, right? It's not a robust model because, as I said, each client has different amounts of data and different, all these issues will definitely arise within the client's data, like, you know, unavailability, imbalance, quality, quantity, whether the data has pre-processed or not. It just because we as an outsider, as a server, let's say, we don't know what kind of data the client is training or what kind of whether it is using rich data or not, whether it is using balanced data or not. All that will have a drastic effect while we do aggregation, because we are considering equal, we are giving equal weight to all the weight updates and then aggregating them to come up with a unified model. But that is not a very optimistic approach. We have to come up with, we have to basically, each step of this federated learning is a research area now, starting with initialization of model. So initialization, again, what can be the challenges? We'll discuss each step in detail now. First is initialization of model. Again, we basic all the machine learning challenges that we encounter also uh, will be here. Initialization, we have initialization bias and model complexity, because VG16 is not the model which everyone came up with. Everyone agreed to a image classification model, but not VG16. Who knows, VG16 is not a good model. Maybe it is a very high model which is not even required for two class classification data. So such kind of issues, we have initialization issues. Then in the second step, when the server sends the model updates to each client, there may be, because if you see it's a client server setup, there is a communication channel involved in between. So there may be packet drops, some kind of network issues. Being a computer vision or machine learning, we generally researcher, where we generally consider, assume all that networking protocols will be followed appropriately, and there is no issue with the packet drops and so on. But still there can be issue. Okay, server sharing model updates. In third step, training, this is where the major issues come, because during training, as I said, the client may have high amounts of non-IID data, non-independent and identical distributed data, and when the models trained on such kind of data, will be very much skewed or biased, or will give drastic performance on the test data, non-IID data. And then the major issue is with respect to security as well. If you have came across adversarial machine learning, where there are attacks possible on machine learning models, basically there can be data poisoning and model poisoning attacks possible in machine learning. The same can be applied here as well. If you treat each individual client as each individual machine learning model, it's a centralized machine learning, right? So the clients with malicious intentions or attackers can try to do data poisoning or train the models in the third step using a poisoned data, right? And then when model is trained on poison data, and when it is considered for the aggregation, the aggregated model that comes out will be very, gives us very bad performance. And model poisoning is again the same thing. We are saying that we are trusting that client will train a model on that data, but it does not need to train, right? It can just get that model, tamper some internal parameters, and then based on some kind of model poisoning or model replacement attack, and share back that only model replaced attack, attack the model back to the server. Again, that leads to drastic issues. So such kind of issue can happen, challenges can happen during the training. The fourth step, again, clients sharing the models. It is similar to networking issues. Finally, in the fifth, aggregation and the selection. I just said that clients server selects all the client updates for aggregation, but it need not to be right. Why should I select all the clients? I can select based on some metadata I have, like client one is training on good amount of large amount of data. I can consider client one update. So there is a research area again in federated learning, which is called client selection technique, on what basis clients can be selected, and things like that. Finally, again, client selection is one thing, and aggregation, I just said average cannot be a better aggregation. There can be different aggregation rules. So there are different aggregation rules present again with respect to aggregation techniques. So again, in the presence of some kind of Byzantine workers, which tries to send poisoned model, so there are Byzantine robust aggregation techniques are also available. Byzantine robust aggregation techniques. Then this is again a research area where we call CRUM. So trimmed mean, instead of mean or averaging all the updates, I'll try to sort them, trim the first and last updates, which kind of outliers, and trim only the average only the updates which are in the between. So trimmed mean is something like the median. Why should I do averaging again? I can do median updates as well. So median is again one Byzantine robust aggregation. All of them proved to be some robust to some extent on certain data settings at certain settings. Finally, in the sixth step of testing, again, if you heard about adversarial machine learning, where there are test time attacks attacking the test data, right? So where the model trained on the model tested on poisoned data will again give us bad results. So there is something called evasion attack, or test time attack, or test data attack. So these are basically the challenges. In each challenge is again a research area. As I said, client selection technique, how many clients to select, what is the optimal number of clients to select, on what basis client can be selected, and given the by, if you have some idea that there can be 30% of Byzantine workers in your system and you don't know who are they, and now we have to sample the updates in such a way that those 30% have to be left out. Now only the benign clients have to be considered. So again, that is a research area. Right now, we will try to discuss on a higher level what are the challenges in federated learning. We have discussed the challenges with respect to each individual step, but now on a higher level we will discuss. First is systems heterogeneity. In the sense, each client device may not be privileged enough to have good amount of resources to training the model, right? Some clients may have less amount of resources, less amount of computational resources, due to which it is taking more than expected time to train a model. For example, in this client one is taking, let's say, 1 hour. Client two is also taking 1 hour to train a model and getting back to the server, but client three is taking 10 hours of time. Okay, 10 hours of time. Now, because of that, the client one and client two, which is already trained and waiting for the updated model from the server, has to wait 10 hours to get, server has to wait 10 hours. Again, thereby client again has to, good clients has to wait for 10 hours. So to overcome this issue, one basic thing you can apply is thresholding, thresholding in the sense you put a time limit. The server puts a time limit of 5 hours, and whatever model updates it gets within 5 hours, it will consider for aggregation and it will share it back to you. But the issue here with is again, what if the 10 hours client client which is taking 10 hours has good amount of data which that 1 hour client does not have. So if we consider the 10 hour taking client data, a model trained on that data will be very useful and leads to early convergence of the global model. So there are high chances of such issues. So we can't just go with the thresholding of time limit and then considering the model updates based on that, right? So that comes with the system heterogeneity, and on basis we have to consider that. Then is statistical heterogeneity. Right? In the sense each client may have different amounts of data, as I said, non-IID data, class imbalance data, and now we can't see from the outside what kind of data each client has, and we can't get. Now the model trained on highly non-IID data will be very much skewed and will lead to drastic performance. And in systems heterogeneity, the lagging clients, or the clients which are taking a lot of amount of time, which are called stragglers, that is called straggling effect, and there is a research to overcome this triangling effect. Third is security aspect, or security. As I said, data poisoning attack, model replacement attack, networking attacks, communicational attacks, man in the middle attack, or such kind of man in the middle attack, and evasion attack, test time attack are also possible. So now to overcome that, we have to come up with a robust federated learning system with defenses, and that can overthrow this model poisoning, data poisoning. That is again a research area. Fourth thing is privacy itself. Now, as I said, federated learning has been introduced to overcome the privacy concern, and then it has been proved to be one approach that we can consider to overcome this, privacy concern. But within federated learning, the system is developed in such a way, like client server setup, there can be high chance of data leakage as well. For example, the server can be malicious. We think server is good, but server is on the back end, it is trying to observe all the client updates and do something called model inversion attack, or membership inference attack. Membership inference attacks, both of these try to regenerate data using the model updates. Membership inference is done in a different way. We try to give some model to some data to the model and check whether this has membership or not, just like the name suggests, whether this has been used for training or not. If it is used, if it server valid, then that is a private data which has been generated, right? So regenerating data is again leads to privacy leakage, and the whole process of federated learning goes into jeopardy, right? Now that's what coming up with a defense mechanism, robust mechanism, encrypting the data, or trying to come up with some kind of differential privacy methods to overcome these methods, again a research area. My since we have come up till here, my research area is mostly under the security and privacy of the machine learning, working on both attacks and defenses. Attacks will help you to find out the vulnerabilities, or the model of the federated learning system, what it is vulnerable to. Once you find the vulnerability, you can come up with a defense method. So this attack and defense cycle is like in a defense is in a cycle. So in the sense, so one come up with an attack and another come up with a defense. Now, based on the defense, there can be adaptive attack. That's a attacker adapts itself to himself to come up with a better attack that can overthrow the defense. So it's like a never-ending process. But as we move along, we try to make the federated learning more robust, because this is only one approach. I mean, which helps us to train the machine learning models along with sharing the privacy. So security and privacy is one such concern. And finally, since we are running out of time, I'll just briefly touch upon the research domains again within federated learning. Please note that what all we have discussed in the model centric and data centric approaches are still applicable in federated learning domain, because at the end we are doing the training again here. Okay, I'll briefly note here some domains that you can refer later. Federated, that's zero shot, one shot, few shot learning. Zero shot learning, again, zero shot, one shot, few shot has always developed, I mean, already well known approaches in here, but adding federated learning in this can help in that low working with statistical heterogeneity issue with the federated. And then we have federated again continual learning, again, which is again very popular nowadays. People are working a lot of in these areas. But a continual learning, when you are adapting to new and tasks, the catastrophic forgetting issue in machine learning should be addressed. And in federated learning within the clients, that if the task get updated, how to overcome this issue. Federated continual learning will help. And federated contrastive learning, again, this is one interest research area which I am also interested in. um, like learning through contrast to samples is what helps in positive and negative samples, that the model should be more close to I mean all the basically developing it in a way that positive samples should the model trained on positive samples and model trained on negative samples should be different. So in a contrast to basically there will be a contrast to loss and things like that. Finally, fourth, we have federated reinforcement learning, again, which is again very popular research here. So federated, applying federated in the sense you are trying to make the model robust along with rating, preserving the privacy and training the models in a better way. So I would like to stop it here, in case because we already it's 150 155. So I'll stop here. I'm open to questions, so you can ask any questions. I know I have rushed a bit because of the time. There's a lot to cover.
So am I audible?
Yes, yes,
So I had a question. I asked you previously, like
yes,
I
yes,
wanted to ask you a question.
yes, yes.
So the question was regarding the tracking algorithm,
Yeah,
object tracking algorithm.
yeah.
So I'm trying to use the sort algorithm, simple online real-time tracking algorithm to track the multiple objects present in the image. So the thing is that when I use the sort algorithm, I cloned it using the GitHub repository and all on the this thing call app, but it is giving me error by when I call the sort constructor, saying it is not. I don't know like why it is
You're
not
asking
working on.
very specific, like point in the code and all. I can't answer, but all I can say is there are different repositories in DeepSort. I think there is DeepSort plus plus as well. You have to first check whether whether the GitHub repo you are using is well known or not, whether there are a lot of stars or folks or not. And then it's always advisable. This is how I do. I go through the author's GitHub, not anyone who has reproduced the code and came up with their own version. It's always better to use the author's code, and then there will always be a section of addressing issues and how it has come up with different versions. So you can use the latest version.
Okay, so another question, sir, I had is now some of the so I had a question about human pose estimation technique. Like there is a human pose estimation technique like MoveNet. What it is doing is it is doing the detection first, then tracking, and then the what you call it is pose estimation. But there are some human pose estimation technique like we use a media pipe where we don't need separately doing the detection and tracking. We can directly do the pose estimation by taking the video frames. So there it is not required, no, so to do the separately tracking and object detection.
No, no. There's no such requirement, because one way to do is do detection plus track. Otherwise, do directly tracking. So there are the available methods. You can directly track. Yeah.
And if there is only one person walking in the video, then as per my use case, I don't need to do the tracking, right? For all the cases, I don't need a tracking. If I can detect object is already detected, I can do my uh,
Mhm. Yes.
remaining things with that
Yes.
without doing the tracking.
So there are four things as I was saying: single object, single camera tracking, multi camera, single object tracking. So I'll note it down. So there are four combinations. So this multi-camera, here you see multi-camera, multi-object tracking is kind of hard case to crack. Okay,
Yes,
there
yes,
you
yes.
you know, and there are combinations like single camera, single object, right? And single camera also you can have multi-object. Again, single camera, multi object. When multi object comes into picture, the issue, I mean, complexity increases. And multi camera, single object. Like if in a traffic scenario, if your car gets stolen or if your vehicle gets stolen, there are different at different junction there are different cameras, but each junction's camera should detect that same vehicle moved from previous junction. So that's
So,
multi camera, single object.
so if I'm using single camera, single object, I don't need to do the detection and tracking. I can use
No.
the pose estimation model like media pipe and directly do the skeleton extraction, key point
Yes.
extraction, and do my further analysis, right? So,
Yes. Yes. You can do that.
okay, okay, thank you. Yeah.
Good. Great. It's really nice one. Hopefully, if the participant will raise a question, we will address you later on also. If they don't have any questions, we can post you. Can you address this?
Hello. In the chat. Sorry, sir, I can't hear you.
Yeah, we can post you the questions later also. You
Okay.
can
Okay.
please address it. Through mail, we can communicate to you. Okay.
Sure. 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 Sure.
Thank you very
Um,
much, Naveen. Thank you.
okay. Yeah. Thank you. Thank you so much. Thank you so much for inviting me for this talk, and thank you, audience, for your um, you know for your patience and listening to the talk. Feel free to reach out to me for any doubts you have with respect to federated learning and whatever I have explained so far. I would like to thank Rakesh sir for giving